Flipped classroom video for M3 WJC Pure Mathematics M2.3.7A3, the integration of logarithmic functions. So what you need to look for, if you think your way back to differentials of log functions, you'll remember that the differential of ln x, the Neperian log of x, is 1 over x, and the way to get that is to consider that if you've got y equals ln x, then e to the y is equal to e to the ln x, and e and ln being inverse functions, e to the ln x is just the same as x, so therefore you've got e to the y is equal to x. And if you differentiate implicitly, dy by dx of e to the y is e to the y dy by dx, the differential of that, and the differential of x is equal to 1, so therefore you end up with e to the y is dy by dx is equal to 1, and therefore dy by dx is 1 over e to the y, but e to the y was also equal to x. Therefore we get this, the differential of ln is 1 over x. You don't have to do that every time, but it's worth remembering. And also, if you had a log of a function, you always end up with the differential of the function over the original function for exactly the same reasons as I've just been talking. Okay, so if we've got y equals ln some function in x, raising both sides as exponentials, e to the y will be equal to e to the ln fx, and that right hand side will turn out just to be fx. When you differentiate, that will become f dashed x. E to the y dy by dx equals f dashed x, therefore dy by dx equals f dashed x over e to the y, but that was equal to e f of x in the first place. Bang, off you go. So it always results, almost always results in a fraction. So if you're asked to integrate a fraction, it's almost always going to be a Neperian log, or a multiple of a Neperian log, ln. They're called Neperian logs after a Scots mathematician, John Napier, but they were in use around before that. So if you are ever dealing with a question where you've got some function in x over another function in x with respect to x, the first question you should ask yourself is g of x a multiple of f dashed x? In other words, differentiate the bottom and see what you've got on the top. If it's a straight, it is f dashed x, then it's a straight log function. If not, you need to do some adjustment. That's a very, very common case when dealing with partial fractions, at least typically in one or two of the partial fractions, depending on how many brackets you have to deal with. And I'll deal with partial fractions in M2.3.7E1, so I'll come back to that, and I will use this particular technique at that stage. So I'll give you a couple of examples of what I'm going to look at. So if I'm looking at the integral of 2x over x squared plus 3 with respect to x, I know how I go about it. Might be worth you pausing this video at this stage and actually thinking about how you would approach that one. When you paused it and had a go at it, then if you unpause it or resume, you'll see how I would go about it. So I would always, if I'm integrating this sort, I decide what my denominator is, f of x in this particular case, because it's easier for me to write, although my writing is not what you'd describe as excellent. So f of x equals x squared plus 3, and that means that f dashed x, my differential of that, is 2x. Hence, the numerator of my fraction is the differential of the denominator, and therefore my answer is that it is the log Neperian log ln. Now you notice I've put modulus signs in of x squared plus 3 plus some constant plus the constant because I didn't have any limits in it. And technically the moduli signs, absolute value, whatever you want to describe it as, should be there because log is not defined for negative numbers. A log is just a power, and you can't raise a power, or can't raise a number to a power and get a negative response. So it should always be moduli notation, but if under exam conditions you use brackets, no examiner is going to bulk at it too much. But ideally, get into the habit when you're dealing with logs of using those straight lines, absolute notation, moduli. So, and of course, k is just a constant, so it's the log of some other number. Let's say c, and if I consider k to be equal ln c, then log plus log will be equal to the product of those two things, ln c. Now I've gone to a bracket, but technically it should be a moduli x squared plus 3. So it's not unusual to combine constants of integrations in with your particular value. So remember your log laws all the way through this, and of course they were something that you met earlier in the course. So if I look at this particular one, and again it would be worth you pausing the video at this stage and actually doing some thinking about this rather than just listening to me droning on, but I'm going to drone on anyway. So I've got the integral between 4 and 1 of 5 over 3x minus 1 with respect to x. And you notice my bottom function is much easier this time. It's not a quadratic, it is a straightforward linear function. And of course, we know that if the if I deal with the differential of a linear function, I'll get a constant. So the differential of 3x minus 1 is just 3. But I've got 5 on the top. Now that means it's 5 times too big, so I could whip the 5 outside the front there. But I prefer to have a 3 on the top, because then it would become a nice little log function, behave itself. So if I whipped 5 over 3, because 5 over 3 times 3 is just 5, so just reversing my function work. So I've got 5 over 3, the integral between 4 and 1 of 3 over 3x minus 1 with respect to x. Now the top is the differential of the bottom. It's a straightforward log function. So it's 5 over 3 ln bracket 3x minus 1 between the limits 4 and 1. Notice again I'm being a little bit remiss, I'm not using moduli notation. However, I know that between 4 and 1 this particular function cannot be negative, and therefore it's defined. So I can actually get away with it in that particular case, but do think about what's going on. If in doubt, use moduli notation. So putting in my upper limit, 3 times 4 minus 1 was 11 last time I checked, and 3 times 1 minus 1 of course is 2, and again my log laws apply. Log of 11 minus log of 2 is the same as log of 11 divided by 2, and that 5 over 3 out the front there will become a power, because a log b is the same as the log of b to the power a. Think about all your log laws. So therefore my final answer in this case is ln 11 over 2, which is a positive value, all to the power 5 over 3, which of course is the 5th power of the cube root, which is fairly tacky. You might be asked to actually treat that as a decimal, in which case plonk it on your calculator. There's no way you're going to work that out in your head. There's no way I could work that out in my head, to be honest. So I promised in a previous one that I would deal with trigonometric functions, and we dealt earlier with the integral of sine and cos and multiples thereof, and I promised that I would deal with tan and cotangent, cot. So if you think back to your GCSE, which for many of you is probably maths that you don't often think back to, we know that the tan of x is sine of x over cos of x. And the reason we know that is the definition of tangent is it's the ratio between the opposite and adjacent sides. So, and I talk about here about the magnitude, it's actually the length of the dimensions of the opposite sides. And so what we've got is that we know that the tan of any angle is the opposite side over the adjacent side. But as long as I do the same to the top and the bottom of my fraction, so you notice I've introduced in my next little section opposite over hypotenuse over adjacent over hypotenuse, which is perfectly allowable if you think about how fractions work. But opposite over hypotenuse is the same as sine, and adjacent over hypotenuse is the ratio that gives cosine, the cosine of an angle. So therefore, the tan of any angle is always the sine of an angle over the cosine of the angle. You wouldn't have to produce that under exam conditions, or unlikely, but it's a useful little tool to know. So cot is the reciprocal, dates back to a time when people like myself who didn't have calculators were having to do mathematics. And if you think about the reciprocal of tan, where tan is a decimal, that actually is quite a difficult piece of mathematics to do without a calculating device. Easy peasy for you guys with a calculator, but it's worth remembering that cot, being the reciprocal, will reciprocate that fraction. So instead of being sine over cos, it is cos over sine. And you won't find that written down in your formula booklet, but you do need to remember it. Now, and if I link back to my previous slide that said that if I've got a multiple of the differential of a function over a function, then I've got a log function, I can now integrate tan and cot without any real difficulty. Now these are in your formula booklet. Okay, you'll notice that the integral of tan x is ln sec x with moduli notation. The integral of cot is ln sine. And those are in the formula booklet. And that's fine. It means you can use them under exam condition without having to actually show them. But you've got to understand why those are the case. So if I consider the easy one first of all, which is the more rare one, the integral of cot x with respect to x is identical to, we've just agreed, or I've just agreed, that this is equal to the integral of cos x over sine x with respect to x. You notice the way that I'd actually dotted my I before I actually put it in. F of x equals sine x in this particular case, therefore my f dashed x is cos x. I've got a straightforward differential over the original function, so therefore it is a log function. So I'll get ln sine x plus some constant because I haven't got any limits, and as I did before, ln c sine x. No real problem, straightforward, easy peasy. If I now consider ln tan, sorry, my apologies, if I now consider integral of tan x with respect to x, by the same way as I went before, this is exactly the same as the integral of sine x over cos x with respect to x. My f of x is equal to cos x. Differentiate my denominating function. Now f dashed x, of course, is equal to minus sine x. Right, so you've got to always watch these minus signs, they're little devils. So if I do as I've done before, treat that as minus minus sine x, because minus minus combination is the same as a positive. So now I've set it up so that I will get minus integral minus sine x over cos x, and I've set it up so that the top of my integration is the differential of the bottom. So therefore this becomes a straightforward log function, but I've got a minus sign out the front there, so this becomes minus ln moduli cos x plus a constant. Now do take care with this, because you notice that the WJEC formula booklet gives it in a different format, and I'll just explain that. Why? We know that a multiple out the front of a log function is a power, so therefore my minus ln moduli cos x becomes ln moduli cos x to the power minus 1. Now you notice that cos x does go negative, so therefore I can only consider the positive aspects of that, because logs are not defined for negatives, as I said before. But cos to the minus 1, which is the reciprocal of cos, is of course sec. So this becomes ln sec x plus a constant. You notice in the formula booklet they don't remind you to put that constant in, which I would personally tend to write as ln c mod sec x. If I had limits on here, and my limits were definitely in the positive range, and of course they would be radian measure, then I could get away with a bracket technically. But if at all in doubt, put the moduli notation in. Ln tan x, the integral of ln x itself with respect to x. So my little graph here is ln x, and clearly there's an area underneath it. It's not defined at x equals 0, because there's nothing you can raise a number to, no power you can raise a number to and get 0 as a response, so therefore it's asymptotic to that y-axis. It's tending towards 0, but it never actually achieves it. But there are clearly areas underneath this particular curve, so I could easily find, for example, the area between 4 and 3, the curve, and the x-axis without any real problem. Got a little bit more of a difficulty with the undefined value when x equals 0, but there are ways around that sort of thing. So it is always possible, seeing as there's clearly an area there, that it's possible to integrate it. Now you could use a numerical method, but those are dealt with elsewhere as well. But it does require a method that we've yet to consider, and that's integration by parts, which is the straightforward reverse of the product rule for differentiation. You know the product rule for differentiation: d by dx of uv equals v du by dx plus u dv by dx, or something equivalent to that. Okay, and I will deal with that in M2.3.7d in parts 3, 4 and 5. So certainly in 2.3.7d part 3 I will introduce this concept of integration by parts, and I promise that I will come back and show you how to deal with the integral of ln x, because there's nothing you can differentiate that will give you an ln. Well, nothing fairly obvious that you can differentiate to give you an ln. There is something, but you wouldn't think of it. So therefore, whilst integration is the reverse of differentiation, it can be quite hard to think what you have to differentiate in order to get that particular thing. So I can use a little trick that I've used a couple of times already in my videos. So the integral of ln x with respect to x is the same as 1 times ln x with respect to x, and this is where the integration by parts comes into it.